Hey everybody, we're going to be starting Unit 5, Video 1. This whole unit is on trigonometric identities. And our first video, you need to have the Unit 5 note sheet available to take notes on. So let's go ahead and fill in this sentence. This sentence can be found, or this explanation can be found on page 186. I just took it straight from the book there, and we're going to go ahead and fill it in first, and that will help us draw our picture and identify our trigonometric functions. So we're going to let x comma y be a point other than the origin on the terminal side of an angle, theta, in standard position. So that actually came from our first unit, where standard position of all angles has the initial side on the positive x-axis and the terminal side somewhere else. So we're going to put a point x comma y other than that's somewhere else other than the origin, and this theta is the angle that is created. So what happens then is that we have, just changing my color, a y value and an x value associated with that angle, wherever it's located. And the y's can be positive or negative, and so can the x's. And we get r. And r equals the square root of x squared plus y squared, is the distance from the point on the origin. That's actually our Pythagorean theorem, or the distance formula, because we're going from the origin. So you'll notice that x squared plus y squared would equal r squared. Well, I take the square root, and r is the distance. So this actually gives us the basic 6 trig functions of theta are defined as here in this box. So sine of theta equals y over r. Cosine of theta is x over r. Our tangent of theta is y over x, so long as x is not 0. Our cosecant of theta is the reciprocal of sine, so that's r over y, where y cannot be 0. The secant of theta is r over x, as long as x is not 0. That's our reciprocal of cosine. And cotangent, being the reciprocal of tangent, is x over y, so long as y does not equal 0. Well, notice I commented on the denominator of all of these 4 functions, but I did not mention the denominator of the sine and cosine. In those 2 functions, the denominator is r. Well, we're not going to worry that r will ever be 0, because r represents the distance from the origin. If r was 0, then there would be no distance from the origin, and the point would be at the origin. In our very first sentence, we said the point had to be a point other than the origin. So r will never be 0. Another big important thing to remember is that r will never be negative. And it can't be negative because r is representing a distance, and distances are never negative. So we know that r will always be positive. Okay, so let's go ahead and draw this picture. Well, actually, you've got this picture there for you, but we're going to go ahead and add to it. And I'm going to draw an 2 radii, where we're saying that this is theta, but if we were to go in the opposite direction, we would just have negative theta. So those angles are the same in measurement, but different directions. So that negative was just giving us a direction. If these are radii of the same circle, then the r values are the same. And therefore, our y values would be the same, but opposite. And our x values would still be the same. So what this tells us is that if I were to take the sine of negative theta this direction, I would have negative y over r. But that should be the same sign as just taking the opposite of the normal direction in the counterclockwise position, because my y values are the same. They're just opposite in direction. So this establishes our first negative angle identity. The sine of negative theta is equal to the opposite of sine of theta. And I'm going to use the word opposite here, not negative. Then I will have the cosine of negative theta will actually equal just the cosine of theta. Tangent, very similar to sine, is negative theta is equal to the opposite of tangent of theta. And we can look more at those in class tomorrow. Your reciprocal identities. We've actually talked a lot about reciprocal identities already in class. Let's go ahead and define them. Cotangent is 1 over tangent. They are reciprocals. The definition of reciprocal is 1 over itself, the reciprocal of a function. So then I'm going to have, let's erase that. Going to have secant of theta is defined as 1 over cosine of theta, and cosecant of theta is equal to 1 over sine of theta. Well, these can be said in different ways, so I'm going to write the first one and I'm going to ask that you complete these other two. I can say that tangent is equal to 1 over cotangent of theta. Do the same for both the secant and cosine and the cosecant and sine. The quotient identities. There are two quotient identities, and we've definitely discussed these in class. If tangent of theta is equal to sine of theta over cosine of theta, then cotangent of theta is also equal to cosine of theta over sine of theta. Those are all your quotient identities. That's it, just the two of them. Our last set of identities are called the Pythagorean identities. I'm going to go ahead and write them for you, and then we're going to discuss them. The first one is the sine squared of theta plus cosine squared of theta equals 1. It's important that you recognize that it's the function that's being squared and not theta. I'm not squaring the angle. I'm squaring the function itself. The second one is tangent squared of theta plus 1 equals secant squared of theta. And the last is 1 plus cotangent squared of theta equals cosecant squared of theta. So what I'm going to ask you to do with the rest of these boxes in this table is to actually rewrite these using some algebra. In this section, or in this chapter, we're going to be doing a lot of manipulation. So we're going to have to be able to see the Pythagorean identities from different perspectives. So if I were to subtract sine squared of theta to the other side of the equation, I would be left with cosine squared of theta equals 1 minus sine squared of theta, because I subtracted the sine to the other side. Had I not done that, instead I decided to subtract the cosine to the other side of the equation, I would have been left with sine squared of theta equals 1 minus cosine squared of theta. I'm going to ask you that you go ahead and repeat that for both of these, writing each of the other Pythagorean identities in two different ways. You can pause the video to do that. Okay, so here comes some practice. So we're going to use the identities that we just discussed, and you can look over your worksheet as we're doing them, to write these expressions in terms of sine and cosine. So our first goal then is going to eliminate all of the other functions, because everything can be written in terms of sine or cosine. Given that secant and cosecant are just 1 over sine or 1 over cosine, and tangent and cotangent are quotient identities, sine over cosine or cosine over sine, everything can be written in terms of sine and cosine. So secant squared of theta is actually going to be written as 1 over cosine squared of theta. And tangent squared of theta is going to be written as sine squared of theta over cosine squared of theta. Those are just the definitions. The first one I was using a reciprocal identity. The second piece here I was using a quotient identity. Just because it's squared does not change anything. Now I'm going to simplify. I'm going to combine the numerator because my denominators are the same. So I will have 1 minus sine squared of theta over cosine squared of theta. This is part of my simplify step. And then I noticed something that we just did in the Pythagorean identities is I wrote my Pythagorean identity involving sine and cosine, and this actually is equivalent to cosine squared of theta over cosine squared of theta, which simplifies to 1. Alright, now I'm going to do the same thing over here with our cotangent over secant. So I'm going to take the cotangent and I'm going to write it in terms of sine and cosine. So the definition of cotangent is cosine of theta over sine of theta over 1 over cosine of theta. Well, using what we know about dividing by fractions, this is really cosine of theta over sine of theta times the reciprocal, which is cosine of theta. So this simplifies to cosine squared of theta over sine of theta. There's no other way to simplify this more. I've got it in terms of sine and cosine, and I've simplified it completely. So this is my final answer for number 2. Number 3. I'm going to go ahead and write this in terms of sine and cosine, and then we're going to distribute. So tangent squared of theta is sine squared of theta over cosine squared of theta by definition using a quotient identity. 1 plus, and this is cosine squared of theta over sine squared of theta using another quotient identity. I'm now going to distribute. That will give me sine squared of theta over cosine squared of theta plus sine squared of theta cosine squared of theta over cosine squared of theta times sine squared of theta. But the second fraction right here actually simplifies and cancels out, and I'm left with plus 1. It doesn't disappear completely, it reduces to 1. So my final answer in terms of sine and cosine is sine squared of theta over cosine squared of theta plus 1. My fourth example, I have cosecant. The first thing I'm going to use is a reciprocal identity, and that is 1 over sine of theta. The second thing I'm going to use on the cotangent is the quotient identity, and that is cosine of theta over sine of theta. In a previous example, when we had common denominators, we were able to combine them. Combine the numerators. So I'll have 1 plus cosine of theta over sine of theta. There's no way to continue to simplify this because I don't have anything squared, so I cannot use a Pythagorean identity, and I have everything in terms of sine and cosine. So that one is done as well. Please review these identities as we'll be using them for the entire chapter. Extremely important that you become confident with being able to replace these using the definitions, using reciprocal identities, and your quotient identities. And of course, when we get into working more with them, you'll see a strong use in our Pythagorean identities. See you in class.